So we will have now the second talk, and the talk will be given by Enrico Priolo. Enrico received mathematical degrees, he told me many years ago. He's a senior scientist in the National Institute of Experimental Oceanography and Geophysics, so here in OGS, our guest. And he's working here since 1984. He has been director of the OGS Seismological Department from 2003 to 2008, and he is currently vice director of the same department. We all know that all the studies of Enrico contribute especially in numerical simulation of earthquakes, seismic site response estimation, geophysical studies for seismic microzonation, and also in the use of temporary seismic monitoring network. But in the last decade, Enrico focuses research activity, especially on seismic monitoring on anthropic activities of induced and trigger seismicity. Enrico is now responsible of 2 seismic networks for the monitoring of underground gas storage activities in Collalto, here in northeastern Italy, and Conegliano Laudense in the Po Valley. So he is also member of a group of experts which is being appointed by the Italian Ministry for the Economic Development for writing up guidelines for monitoring of underground activities. So we welcome the talk of Enrico. Thank you. Just a small reminder, please switch off the telephone. Thank you.
Thank you, Stefano. Good morning. Just a moment, I put my telephone to have the time. I would like to thank the ESC for inviting me to give this talk in conjunction with that of Bill Ellsworth. In my presentation, I'll develop the following theme. In Europe, underground activities related to the energy development always imply a not negligible level of risk. So fundamental tools and steps for improving activities, operation safety are high quality monitoring network and reliable discrimination methods in order to be able to intervene at a very early stage of the microseismicity appearance. This map shows the sites where human activities have generated in earthquakes with magnitude greater than 1.5 in Europe. Sites are classified according to the activity type, and I have shown in the map also the sites, some well-known sites where induced seismicity have been recorded. In the last year, you see some famous cases such as Groningen, Blackpool, Basel, the Castor project, as well as Valdagri. Obviously, they are famous in Europe, and all these cases have in some way been discussed or just mentioned in some previous presentation in the last days. One case that is worth being added here is that of the Emilia earthquake, although it hadn't been induced or triggered, but I speak of it in more detail later. The Europe features, here I compare the previous map to those of seismic hazard and population density respectively. The Europe features an uneven distribution of seismic hazard. The central and northern countries feature a moderate to low level of hazard, while its southeastern countries as well as Iceland are exposed to strong earthquakes. On the other hand, large part of Europe is densely populated, and it has a historical heritage of great value that must be considered, obviously. And most activities involve areas with tens to hundreds of thousands of people locally. Let's see how those elements come together now. In areas of high level of hazard, we have a high probability to find some active faults near human activities. On the other hand, in areas where the hazard is low, we have a high proportion of vulnerable building due to a lack of seismic design requirement. In all cases, high population density, vulnerability of historical and artistic heritage, as well as an amplified perception are all issues that must be taken into account. On the left side, you see that in areas most exposed to earthquakes, the main concerns are those for triggered, possibly devastating earthquakes, and we need there some reliable discrimination tools between natural and induced seismicity. On the other side of the screen, you see that the main concerns are for induced earthquakes, the reactivation of silent faults, and the priority is that for updating seismic hazard and design. In all cases, the identification of earthquake causes and the assignment of possible responsibility is our main issue, and this is not trivial, obviously. I want to speak now of the Emilia earthquake. It struck an area which is considered of moderate seismic hazard by Italian regulations. You all know that it had two strong events at 9 days of distance each other and caused 27 casualties and about 15,000 homeless. But above all, it had a strong impact on the economy. The Emilia earthquake raised dramatically the issue of the seismicity generated by human activities with the relevant aftermath. Few days after the earthquake, rumors and false information circulated about fracking as a possible cause of the main shock. But fracking has never been done in Italy. Then suspicions were addressed towards some underground activities, namely the oil production and water injection at the Cavone oil field, and the geothermal exploitation at the Casaglia reservoir near Ferrara. It took more than 2 years, the work of 2 international groups of experts and some further scientific studies for ruling out that the main shock had been caused by human activities. Now I want to give you some facts. In February 2014, the international commission named ESC stated that it could not be excluded that the activities carried out in Cavone oil field could have been the cause of the earthquake by triggering the earthquake. Less than 2 months later, the Emilia-Romagna region had to stop. It stopped because of this resolution, let's say, all new requests for hydrocarbon production or exploration. During the summer of 2014, another group by Astitz et al. Demonstrated that the pressure changes induced by the fluid reinjection into the reservoir were too small to trigger any of the 2 earthquakes. Finally, another study in 2015 by Dam et al. Confirmed that the main shock was neither triggered nor induced by the activity. All studies suffered from a lack of experimental observations as a result of poor specific seismic monitoring. In practice, there was no chance to detect any microseismicity in the region between Cavone and the main shock. For that reason, ESC recommended developing high-quality monitoring and discrimination techniques for hydrocarbon-related activities. So my conclusion about the Emilia earthquake in conjunction with the induced seismicity subject is that it is possible but hard to do any discrimination without good data. It is impossible to adopt any decisional protocol without real-time data and analysis, and we absolutely need to develop high-quality monitoring system. The next topics will be discrimination of the different kind of seismicity, high-quality seismic monitoring, and some words about the monitoring guidelines and the decisional procedures. In the last 25 years, several approaches to discrimination have been developed. They can be classified into qualitative. You probably know several of these works, of these papers, into statistical, seismological approaches, correlation-driven, I would say hardly correlation-driven. In any case, most methods rely on the capability of correlating the seismicity to the industrial activity in the space-time domain. Unfortunately, the pure operation of correlation is not enough to decide whether there is a cause-effect relationship between two phenomena, as you well know. So we must support correlation by a suitable physical framework. For that reason, physics-driven approaches have been developed. They are based on modeling the pore pressure diffusion, possibly, and if it would be possible to calculate the Coulomb stress change and then to go towards the synthetic seismicity catalogs of the time of the type of the stress rate and state seismicity. Now I speak about microseismicity and fluid diffusion. There have been several works about this relationship between these two phenomena, but I show here what have been done by Shapiro and Diska in 2009, where they clearly show that the fluid diffusion within rocks with moderate to low permeability generates a microseismicity that diffuses, that is, migrates in space and time together with the fluid. They have given a way to interpret whether the seismicity is induced or not. And this is done in a time versus space diagram, where the space is the distance from the injection well. And in this diagram, if you plot the seismicity, you can consider it as induced if you are able to find a curve, which is a parabola, which acts as an upper bound to the seismicity cloud. The curve should start at the beginning of the seismicity, let's say, appearance. You can also see here the back front of the seismicity, which is due when the fluid flow stops. The parabola corresponds to the fluid front diffusion, and it is also called a triggering front, and it depends from the hydraulic diffusivity. This kind of interpretation has been extensively applied to activities that generate fractures, such as hydraulic fracturing or geothermal stimulation. But it may fail for triggered seismicity on existing faults, because you can see here below, in this case, you may have clouds of seismicity that are not directly connected to an origin, to a microseismicity appearance, to, let's say, the fluid diffusion phenomenon. So in this case, you need to calculate the pore pressure perturbation to establish a possible relationship, cause-effect relationship between this seismicity and the fluid diffusion, and calculate whether the pore pressure perturbation is able to trigger the earthquake. A clear illustration of the previous concepts has been done by a work, experimental work by Kern and et al. In 2014, where they show that the seismic swarms occurred in Oklahoma in 2011-12 were due to the fluid diffusion away from high-rate wastewater disposal wells. And they showed also that the strongest seismicity was triggered several months after the injection at distance of several kilometers from the injection wells by quite small pore pressure variations. So this figure here agree completely with the image that Bill has given a few minutes ago. Mularja and Bizzarri explained by a theoretical study the mechanism that drives the delayed trigger distance, which is the slow propagation of pressure fronts along drained paths towards critically stressed faults. Thus, they claim, it is illusory to control earthquake triggering by close monitoring of minor foreshocks, since induction may occur with a delay of up to several years. Obviously, you have to mean here that the term induction is a broad, has a broad meaning of triggering. So a big question is, against this, I would say, dramatic conclusion, to what extent may fluid diffusion not generate any microseismicity at intermediate distance? In my opinion, a very sensitive network is able to detect the microseismicity at its early appearance. So, in most cases, I would say. As a matter of fact, Oguari et al. In a very recent work showed that by reprocessing local network data recorded in Arkansas, they were able to improve the existing catalog by 2 degrees of magnitude, and they found that in this new catalog, the microseismicity started 1 month ago earlier than previously estimated, and the microseismicity was able to indicate the fluid diffusion at depth. Now I want to compare the 2 different approaches to, so in the previous slide you have seen the importance of a high quality seismic monitoring on detecting the microseismicity at a very early stage of appearance. So I want to compare here the 2 approaches of seismic monitoring by industry on the left side and by the seismological institutes or community on the right hand side. Industry, the goal of industry is that of studying fluid diffusion within reservoir and enhancing production. Their networks are made by geophones, possibly arranged in arrays, or always I would say, and if possible deployed in downhole at depth. The results are strictly oriented to industry, and they are delivered by internal, restricted, I would say, reporting, mainly. On the other side, you see the point of view of the seismologists. The goal is the earthquake protection, this discrimination between induced or natural seismicity, as well as ground motion reporting in the case of stronger earthquakes. Networks are made by seismometers, usually deployed at surface, but if possible at shallow boreholes, and accelerometers. Results are oriented to both the industry and public, and this makes not so few problems usually. And we all would like to have open access data, so this is a priority. This is an example of high quality seismic monitoring, which is really important in my opinion, is that in Groningen the network is being it's now under development and will probably be ready within this year. It has about 60 stations with 4 borehole geophones, at different depths, one accelerometer at the ground surface. The goal is to reach excellent sensitivity and excellent data quality. The KNMI, as a public research institute, manages the monitoring on behalf of the industry, and the waveforms are freely available on web. The other example is that we manage here in OGS is the Colalto network, which is used to monitor the seismicity for a gas storage in a depleted reservoir. It has 10 borehole stations, which are integrated by a number of regional stations. But the peculiarity here is that the area is located in an area which is exposed to strong earthquakes. It is an area with a medium to high level of seismic hazard in Veneto. After 4 years of monitoring, the Colalto network has located 10 times the number of earthquakes than the regional network, and the image of in the same period, obviously, and the image of seismicity that we have now of the area illustrates or shows very clearly the compressional structures, faults, which are active at the front of the South Alpine, front. You also see in the upper panel here a distance of 3 kilometers from the reservoir, which is represented here, which is a reference distance for the Italian guidelines in order to tell whether the seismicity may be induced or not. In order to be sure that the recorded, located seismicity has a natural origin, we have performed a numerical modeling of poroelastic pressure diffusion with a model which is quite simple, but it is also quite conservative with respect to what happens in the reality. And what you can see very quickly here is that the seismicity, and especially all the clusters of seismicity, fall outside the curve which draws the zero perturbation of the pressure. This is the theoretical diffusion curve. This is with the poroelasticity. And so we can say with no doubt that all the seismicity has a natural origin. Now I want to discuss one of the possible, there are several actually, one of the possible traps in seismic monitoring. And this is the case of the misinterpretations due to a too localized network, such as an industrial one. And I speak about the so-called long period, long duration events, LPLD they are called, which are emergent signals with duration of several tens of seconds, similar to those of slow slip tectonic events. They have been recorded by industrial networks during hydrofracturing in Canada, as well as in the geothermal system at Mount Amiata in Italy. Das and Zobak interpreted these kind of signals or events actually for these authors as cracks induced in particular zones of the reservoir made by shales with a high content of clay and corrosion. So this interpretation is important for the reservoir exploitation. In 2015, last year, Cafani et al. Showed in a paper that these LPLD signals look very similar to those of regional events. And another paper followed this year, very recent paper by Zečević et al. That found correspondence in US array broadband data with many LPLD events up to several hundreds of kilometers away from the injection well. These authors analyzed about 20 events, if I well remember. And the conclusion of their study is that all LPLD events analyzed turned out to be weak regional earthquakes, which were not reported in any catalog before, rather than local events related to the hydrofracturing. So you can see the importance of having a good network, local network with strong integration with the regional stations. Now I'm going to speak about the monitoring Italian monitoring guidelines. Following the Chiesa Commission suggestions, the Italian Ministry of the Economic Development issued the specific guidelines for monitoring oil and gas activities in Italy in the end of 2014. These guidelines define standards for monitoring microseismicity, ground deformation, and pore pressure, with the aim of improving the safety of the activities. Key concepts are detecting microseismicity and natural seismicity better and earlier, discriminating among induced, triggered, and natural events, establishing a proper decision-making process based on the traffic light model, and, important, ensuring transparency and independence of monitoring from industrial company, which is not easy. One of the concepts that have been developed are those of detection domains. Two different domains have been defined. One is the so-called internal domain, which surrounds the reservoir, and it is directly associated to the induced seismicity. Here the monitoring must provide very accurate locations and be very sensitive. Then another domain, so-called external domain, has been defined, which is associated to the possible triggered seismicity and the natural one. It surrounds the internal domain, and here all the elements which are important for the problem of triggered seismicity should be included. So all faults should be, if possible, be drawn, be included inside. And obviously here the aim was to improve the detection with respect to the existing networks in order to have a good image of the natural and seismicity and the possible migration of the seismicity outside of the internal domain. The Italian guidelines have defined a decisional system based on 4 levels, where the level transition is not automatic, but it is based on the analysis of the monitored data. This is an important point, but I have no time to discuss this. But it is important to note that thresholds are multi-parametric, so it is considered not only the magnitude but also the ground motion parameters. Please note the second level, the yellow one, which is called of attention, which is used to switch the let's say kind of intervention of seismologists, which is nearly automatic in the green level, to let's say higher attention with prompt analysis in order to be ready with in the case the seismicity increases up to the orange level. This is my final, before the conclusions, my final slide, where I want to compare how different is, I want to compare 2 different implementations of the traffic light system. One is the case of the Horn River in Canada, and the other one is the Boland Shale in UK, which is the area where the Blackpool site is located, that you all probably know. You can see the very different level of the thresholds and the different principles that have been considered in defining these levels, these thresholds. You see that a quite high level of magnitude has been defined to stop operation in Canada, and the occasion level is between magnitude 2 and 4, which is quite high. And also you see on the right side, the fact that at the occasion level, a sort of discussion begins in order to define how to mitigate, which is the best strategy to mitigate this seismicity. In Blackpool or in Boland Shale, the threshold levels are very severe, and these, I don't know why they are so severe, maybe for some considerations about the acceptable risk, or due to the poor network that they had at the beginning, I don't know. But this level comes out from a review study from of a group of experts, which considered the maximum magnitude threshold of 1.7 initially proposed for the traffic light system undesirably high. So my conclusion are, I start with a trivial conclusion. This is that human activities carried out underground imply a not negligible level of risk. Okay, this is not a good conclusion, I mean, nothing new, but I want to stress here that we all need a very tight collaboration between seismologists and engineers in this to reduce this risk. Key factors for the future, in my opinion, are dedicated high-quality monitoring networks, effective discrimination by integrating statistics and physics-based method, for example, and detection, location, and interpretation of the early microseismicity. This is a very important point. Finally, I want to finish with this statement. I think that we should try to send also to industry this concept to promote public understanding and acceptance of underground activities. We not only need to do the best, but we need to demonstrate that we are really doing the best. So industry and we as seismologists should be able to make people sure that almost, if not all, everything is under control. I wish to thank my colleagues that helped me in the preparation of this presentation, and thank you for your attention.